inviting now Neil Stav. Neil has been a forecaster, also at the unit of the Air Force. He was, in fact, commander of the operational forecasting branch during the years 1987-1993. He has his degrees in geophysics and in physics from Tel Aviv University. He has been working at the Tel Aviv Center of Science Education for 9 years in the area of physics education and e-teaching. For the past 4 years, he has a position at the Israel Meteorological Service, where he is Deputy Director of Operational Meteorology and Director of the Forecasting Center.
Okay.
He will present us.
Okay. Okay. First of all, my lecture will be somewhat different from the other lectures because I don't come from the research community, I come from operations. And therefore, I will not introduce new results or studies, but application of things, and probably I will raise more questions than answers. But this is kind of the things. So maybe I'm more connected to what will happen after the break. What I'm going to speak about is the way we use the radar at the Israel Meteorological Service at the moment. Actually, what we're trying to do in those days. A little bit of things that we're doing in the last few months. This is, of course, only the beginning of something, and I hope it will get much improved. This is Eliakum is the guy behind most of the material you see here. I'm just the presenter. And we are collaborating with many good people, and I will mention it along the way. So I will speak a little bit about warning and early warnings we use in the IMS, which are not very known to the general public because they get many of them get to specialized clients that demand them. And then I will speak a little bit about hail and severe thunderstorm warnings, about flood warnings, and then wind shear warnings. How to use the radar to help issue those kind of warnings. Okay, so the concept we are using is a concept that is common worldwide. This is taken out of the Met Office website. When we talk about warnings, we want to change our customer attitude towards the weather to make him understand that there's no severe weather, or whether he should be aware that there may be some development, or if there's something that really needs now to take action to do something. So we adopted what is called early warning and warning in Britain, early warning and flash warnings. In Hebrew, we call it hatra'ah and azhara. So the idea is that when you talk about being prepared, then you want to that it will happen several hours in advance, or maybe even a day or several days in advance. And when you're talking about something that is really you must take action now, then this is the warning or the azhara itself. Okay, so for those visitors from outside, there are times that there is hail in Israel, not only sunny skies, not too often. And this can be, of course, detected by radar. Actually, a few years ago, I met Mr. Barbosa from the Portuguese Meteorological Service that told us the way they use the radar and their warnings. So we decided to adopt their concept and try to see how it works in our region. They use for hail, as you see the definitions here, they take a vertically integrated liquid of more than 5 and tops 45 dBz above 3 kilometers, and all those thresholds should hold in a threshold region of 10 square kilometers, and then they have an automatic warning. We tried it, and it probably is okay. We changed a little bit the threshold area and the field, but basically we adopted this scheme. They also have severe weather warning levels that try to indicate that this is a severe storm, that something it's not the usual thunderstorm. One of them is this is based only on dBz. We adopted their high severity index, but for the lower severity index, we chose a little bit different method of combining again something more similar to the hail, both the vertically integrated liquid and the tops. Now, a little bit about why we chose two separate methods. This is the scan levels of our radar, and here's the point to say thanks to Yoav that helped us configure the scan about a year ago in a better position. The idea is to have a scan that allows you both to detect things far away, but also to have detailed information of the nearby environment. So the idea was to have a good coverage, volume coverage on the 140 kilometer range. I will show in a minute. It means most of Israel, and yet to have some information also about faraway places, even if you have one angle over there. So we have this scan happening every 5 minutes, and allowing us a detailed picture of clouds in this region and some information on clouds even far away. So this is an example of the 280 kilometer scan, and you see that it covers all of Israel, including the Bay of Eilat here down, of course, it cannot really detect the details of clouds so far because the lowest angle, 0.3, is already about 4 or 5 kilometers high in this region. And yet, if you have intense thunderstorm in this region, you can see it. And this is an example of a month ago where there was a nice thunderstorm arriving to the vicinity of Da airfield and caused there a series of microbursts, and it could be easily detected by simply the one scan. So for such a region, the region of more than 140 kilometers, the only way to issue some warning of severe clouds will be to find some threshold, let's say of 50 dBz, and above this threshold to issue a warning. This is the simple scheme. For the 140 region, we can also check the veil and the tops and get a more complicated index. So here you see an example of the 140 range, and you can see that in this range we can have the tops and the cross sections and everything because of all those angles. Those of you who were yesterday, we were talking about the January 17th of January weather event when we had development of thunderclouds coming from the south. This is a special picture for Baruch, who was talking about this tropical plum, or the warm, Asaf talked about the warm conveyor belt here. But I want to focus really on those clouds and to see how this warning scheme works. So you see here the slide. This is the way it appears on the screen. You have the clouds, and whenever a threshold is crossed, you get a symbol. And here on the bottom, you see the details. This is a Sigmet system, and it's built inside. We are simply using the options offered by the system itself. So you see here those clouds approaching from south. Once it will cross the 140 range, then also a more detailed information can be gained, and then there is also an issue of hail. So before that, there was no hail warning, and then it appeared. And you see here those several clouds with all those warnings appearing and disappearing as those clouds move forward. Now the question is, of course, how to validate such things. So it's nice to put in those boundaries, but how to know that it works? Well, hail observations are not very common. If you look on synoptic stations that give you observations in 3 hours, you will not be able to find much. Even in the Air Force or the on the airports, you don't get a lot of information about hail. We found that we use our dysdrometer in Bedagan. We can see events of hail which sometimes last only 10 minutes or so, and you can see it happening. And maybe once we'll have more of these scattered around the Earth, it will be easier to check such a algorithm. At the meantime, we checked it by looking at what happened at stations, which we have a lot of stations scattered around the country, when those clouds pass over. And you see here a demonstration of this cloud where we followed it from Sinai towards Ashkelon in this case, and what kind of things happened at Ashkelon port when it passed over. And you see this gust of, the scale is meters per second, so it's a gust of almost 40 knots. Rain intensity in 10 minutes of 5 millimeters in 10 minutes, and a sharp drop in temperature, all indicators of strong gust and strong activity. Is it enough to call it a severe thunderstorm or not? We will have to see more case studies and to see if it's a good definition or not, but at least we see that those clouds indeed have strong signature in our stations. Another example, again from last year. This is the event of October last year. You see here the Air Mass picture, and you see the radar. You see here a very intense signature in the radar, and here we see a line approaching, and of course with all the warning triggered. And this is the case where we saw the SEV2, the more severe warning appearing, and it's not surprising. And if you look on this cross section of this cloud, reaching about 50 dBz, reaching almost 9 kilometers. Of course, the question is whether this thing indeed was severe. And again, the signatures are quite clear. You see again gusts of about 40 knots. You see a dramatic change in the wind direction, a drop in temperature, a peak of precipitation, etc. Okay, how much time do I have? Because we started late. 5 minutes? 5 minutes, okay. I'm saying 5 minutes because it's now the topic I really don't have much to say about, so I'll do it. Okay, so flood warnings. Well, actually, when we bought this Signet system, we were thinking a lot about flood warnings, and we bought it with a system that you see at the moment on the screen, which allows, these are the river basin in Israel, and this map was given by Amir Givati from the Hydrological Service and implemented inside the system. Each catchment region collects the amount of precipitation as indicated by the radar, and can show, here you see 4 different catchments, and you see the graph of precipitation in the last 12 hours. And you can also issue a warning once some threshold has been crossed. But when we tried to play with it, we understood that it's really much more complicated than just setting a threshold, especially in the regions where flood warnings are most critical. And the regions where these are critical in the region of the Judea Desert, where you see here pictures from a flash flood in Qumran region on May 2007. The issues of Judea Desert, and this is I'm here using on the right the slide from Amir, on the left the slide from Efrat Morin of the Hebrew University in Jerusalem. Both of them try to help us understand better the issues of floods. So, okay, it means that it's lunchtime, right? Okay. So you see that this is the Dead Sea, and you see those very, very small catchments. And it means that those basins are very small. The Qumran, for instance, is only about 40 square kilometers, so it's one of the smallest, but still you can see the typical sizes for about 100 square kilometers. If you look on the slopes here, you get from 700 meters to minus 400 meters within a scale of 15 kilometers, so it's very steep slopes. And this is not, on the top here there is a soil, but this is rock. So actually what you get is a combination, quite lethal combination, small catchments, rocky ground, steep slopes, high rain intensities, and now the combination means that a very fast response when you have even an isolated cell, and immediately you can get flooding. And you see here this very dry place suddenly develops a flow of hundreds of cubic meters per second within less than an hour. And this is, of course, challenging because it's not like you have a basin, and if we return to the concept demonstrated in this picture, you are taking a basin and then you start summing the rain for several hours, and then you issue some warning. This is not the case here because a single cell, and this is the Qumran region, and you have here the measurements in this region at this day. So you have, this is the region itself, and here are the measurements. And you can see that, of course, none of them is inside this small region. If we had to estimate how much rain was inside just by interpolating those numbers, and this is a very dense net of rain gauges relative to what is common worldwide. We are talking again, this scale here is about 15 kilometers, 20 kilometers from here to here, and a lot of measurements, and yet none of them really telling you what's happening here. And when you take the radar, you see that actually most of the rain in this region was here. So this 15 millimeters is only an underestimate of what actually was inside. And you see it's a very small cell only on this region, but it was enough for the flood. Here you see the estimated precipitation amount, and you see this is without calibration. There's a lot of work to do here in calibration. And you see that it's not giving a proper estimation. This is, of course, because it is there is the mountain range over here, and we don't see the bottom of the clouds properly. But we see here the pros and cons of radar use in this aspect, and this is you can see the rain in regions where you don't have rain gauges, but to get a quantitative assessment in such regions is not simple. And I will add the additional thing that if the entire phenomena is 1.5 hours, like development of typical cloud, and this is enough to cause a flood within less than an hour, until you will wait and see this cloud developed and a threshold crossed, you will not have enough time to warn anybody about it. So actually, at the moment, we are not using the radar for issuing those warnings, but we use our understanding of the situation, of the synoptics, of the stabilities, of the moisture flux, etc., in order to issue those warnings. Okay, so I'll skip here the most of this and just say something about wind shear, and I'll finish. So actually, when you use Doppler, you can see the wind. So this is the Doppler shift, some ideal pattern that should occur when you have, in this case, westerly winds. You have a shift to the blue on one side, shift to the red on the other side. This is if situation is simple, but when you have a situation of wind shear, then you have a more complex structure. I will skip a lot of things and just show you a line that is arriving at the seashore, and along this line, a very complex picture of wind. You can see here the detection of this squall line and its movement, and actually you can use it for wind shear detection. And it's validated versus the observations. Okay.